Hello everyone. Let's have a look at one example for design of Kettle reboiler to practice some of the concepts that we talked in the lecture. So here we are designing a Kettle reboiler, and as such we are supplying 0.1 kilomoles of vapor from a distillation column, and the column bottom product is pure butane. So for example, butane is coming from the bottom of the distillation column and entering in the shell of this Kettle reboiler. And because butane is pure, so we can actually calculate its critical pressure using thermodynamic data. So the critical pressure of butane is 38 bar, and we also know that the column operates at a pressure of 19.25 bar. So that is PC, and this is the operating pressure of the column. At this pressure, the butane vaporizes at a temperature of 112 degrees centigrade, and the vaporization can be assumed essentially isothermal, as you know that when the liquid changes its phase, it's an isothermal process. So here we know that outside these tubes, the vaporization is happening, and it is happening at a constant temperature of 112 degrees centigrade. While inside the tube, we are using hot fluid to heat these liquid to convert it into vapor, and that hot fluid is actually also steam. And steam, you know that is also condensing. So it comes and gives its heat to the liquid, vaporize it, and then condense itself. So we are having vaporization outside the tube, but we are having condensation inside the tubes. And the condensation temperature is at 140 degrees centigrade. And again, it's a constant temperature. So the film coefficient, including the fouling for the condensing steam in the tube, and the fouling factor of vaporization can be assumed. So here we have the film coefficient plus the fouling factor for the condensation that is inside the tube. So we have this value, and then for outside the tube, we have the fouling factor of vaporization. Okay. So in this value, we have the film coefficient of condensation plus the fouling factor included for the tube itself. The critical heat flux of the tube is estimated to be this value. So we know the value of QC, the maximum possible heat flux, and the boiler is designed to operate at 10% critical heat flux. So we have a safety factor of 90%. Steel tubes are used with 30 millimeter outside diameter. So you know what kind of tubes you are using, what are their sizes and dimensions, and you know the conductivity of the material, that is 45 watt per meter per Kelvin. You have to calculate what is the overall heat transfer coefficient for this Kettle reboiler. Okay, so if you pause the video and try to solve it yourself, and if you do not manage, then have a look at the solution. So we are required to calculate the value of U, okay, or the U based on the outer diameter of this boiler of the tube. And we know this long equation that we derived in lecture 7, where we are looking at the contribution to the convective heat resistance, fouling resistance inside the tube, conductive resistance of the tube, fouling resistance at outside the tube, and then the convective resistance outside the tube. Okay. And from the data that is given to us, we know that we have the value of HI. Okay, so the heat transfer coefficient due to condensing steam, HI, is given to us, but at the same time, actually the effect of convective transfer inside the tube and the fouling resistance are given together to us. Okay, so this part of the data, this part of the equation is known to us. Okay, so we know the combined value of this resistance here and this resistance here. We know the conductivity of the system, we know the dimensions of the system, and we know the fouling outside the tube. So we know this part of the equation is also given to us. What is not given to us is the value of H node. That is the film transfer coefficient of vaporization at the outer surface of the tube. Okay, so we have to calculate the value of H node. And if you remember, we can use the equation of NB, for example, equal to H node, and we can find this value. So let's see how we can do that. Now to find the value of NB, we need to know how much heat is being transferred, or how much heat is being, what is the heating load of the reboiler. And we know from the question that we are given what is the critical heat flux. And we are also told, sorry, we are also told that we are operating at 10% of the critical heat flux. And as such, we can calculate what is our operating load. So our operating load is QS 0.1 times QC. So we get a value of 6 10 to the power 4 watt per meter square. So now we know the value of QS, and we need to calculate the value of H and B or H naught. So we are, because we are considering vaporization happening at the outer surface of the tube. So if you look at your lecture, we discuss Palin's equation, okay, and we can use Palin's equation, that is H and B, and this equation is used for pool boiling, and specifically in pool boiling we are looking at nucleate boiling. Okay, so if we approximate our Kettle reboiler that we are in the pool boiling and we are kind of considering nucleate boiling, we can consider this equation. So this equation requires the value of PC that is given to us. We need to know the value of operating pressure that is also given to us. We have just calculated QS from our critical heat flux. So this equation, all the variables are known to us now. So if you put the values from the given data, for example, here we have the operating pressure, here we have the PC, the critical pressure. So we get the value of H and B. And as I said, that this H and B actually, in our case, is equal to our H naught. Okay. And now we can use this value of H naught or H and B and feed it to this long equation for overall heat transfer coefficient, and as such we can calculate what is the overall heat transfer coefficient here. So now let's look at that equation. So we know this long equation here that we write before, and we know the data either that is given to us or we calculated. So we know the outer diameter of the tube, we know the inner diameter of the tube because we knew the thickness of the pipe. So we can calculate outer diameter minus 2 times the thickness, we get the inner diameter. We know the conductivity of the wall because it was given to us. We have calculated H naught, that is equal to H and B. We use one of the correlations that we studied in lecture, Palin's equation. We know HI, so that is actually the effect of HI plus FI. Okay, so this is a combined coefficient for the heat transfer coefficient inside the tube plus the fouling effect inside the tube, and that is given to us as 5700. And then we know the fouling coefficient at the outer tube. Okay, so we know all the parameters that we require to calculate U. So we can actually cancel out this part here, okay, because this part now is included in HI here. Okay, if we do that, we can simplify this equation like this. So we just actually delete this part of the equation. So we have now a bit more simplified equation. All the parameters are known to us. So we just have to put out the values. So if you plug the values in the equation, we can get what is the value of U naught. Okay. So we have, so that is for 1 over U, and if you calculate U from it, so we have it. We know the overall heat transfer coefficient. Okay, so the rest of the design for a reboiler will be just exactly like we did in heat exchangers. Okay, so once you know the value of U, you go back to your equation. Q is equal to UA delta T. Okay, so delta T Lm So you have to calculate the value of delta TLM. You have to either calculate Q, okay, or you have to calculate A, okay, and you have to find out the value of U. Okay, so in this case, we have the value of U, and if Q is given, we can calculate the value of A, and if A is given, it means that is a rating problem, so we can just calculate the value of Q. Okay, so the rest of the design from this step onward is exactly the same as we did for a routine heat exchanger. Another important thing to memorize, that is kind of can be a situation that in this case, for example, we were given the value of HI and we had to calculate the value of H naught, and we did that by using H and B. Okay, so we use one of the equations from reboiling, but you might be in a situation like when you are designing a condenser, for example, when you need to calculate the value of HI. So let's say the condensation is happening inside the tubes. So like what was the case in this example, like steam is condensing inside the tube, and you don't know the value of HI, but you know the value of H naught. Okay, so in this case we have to use the equations that we learned for condensation, and we have to use Nusselt equation. For example, one of the correlation is Nusselt equation, where we can calculate HC depending on if the condensation is happening inside the tube or outside the tube, if it is a vertical condenser or a horizontal condenser, and then based on that we can calculate HC, and this HC should be equal to HI. And just like this example, once we know HC or HI, then we feed our value into this long equation of U, and as such you can calculate U naught. Okay, so that is another scenario. You might have another case, that is, let's call it case number 3. So that was case number 1 here, that is case number 2 here. And you might be in a situation where actually you don't know the value of HI and you don't know the value of H naught. Okay, so you don't know both of these inner and outside heat transfer coefficients. So what we can do in that case? In that particular case, you have two options. One option is that you calculate, if the data is given, then you can calculate HC if, let's say, condensation is happening on the tubes, okay, or in the shell, whatever. And here, for example, you have vaporization. So you can calculate condensation coefficient by equation for HC, and for H naught, you can calculate H and B just like we did here. And so that is one option. The second option is that you assume some values of HI and H naught based on literature. So there are a lot of graphs and figures that are available for a particular system. For example, if you are talking about organic versus steam heat exchangers or steam condensers, there are a lot of literature based on these systems where people have provided the most suitable values for HI and H naught. So your first guess will be to pick one of those values and then start your design. And once you start your design, it means that from your assumed value of HI and H naught, you calculate U naught. It means that you are kind of assuming U naught. You do your calculation, you find a value of Q and U and A, and you do all your geometry design. After your geometry design, you again calculate the value of U and see if two values of U match or two values of HI and H naught match at the end of the design. It means your design is complete. But if these values do not match, it means that you have to just keep on going, and it's now an iterative process. Okay, I gave you some hint about that in the previous lecture. This is slightly out of the scope of this unit, so we are not going to talk about it, but in actual life, that is how you design, because in most of the cases, we don't know the values of these HIs and H nodes, and then you have to iterate to find a correct value of this, or the final value of these heat transfer coefficients. Okay, so that is all for this example. Thank you for your time.